In our previous lecture, we have derived the Gauss elimination procedure for the solution of a system of linear algebraic equations. We have also solved an example using the method, but we have mentioned that the procedure may fail if the pivot turns out to be, if any pivot turns out to be a 0 or a very small number. Now, to avoid such difficulties, we shall use what is known as a pivoting procedure or pivoting strategies. So, let us discuss what are the pivoting strategies that we would like to use here. The first procedure that we shall use is known as a partial pivoting. Partial pivoting. What we do in this procedure is, when we have our system of equations, the augmented matrix constructed out of it as our A B, then I take in the first step, I take all the elements in the first column, find the largest element in magnitude and bring that as a pivot. That means, we interchange that equation, the first equation, with that equation which has the largest element in magnitude. So, that will be the first step of the in the Gauss elimination procedure. Before we start elimination using the Gauss elimination, we will do this procedure. That means, we will say in the first stage, the first column is searched for the largest element in magnitude, for the largest element in magnitude, and we bring this as a pivot and brought as the pivot by interchanging the first row with that row having the largest element. Now, you can note that if the first element is 0 or very small, then we are automatically avoiding that particular division by that particular pivot, because that element which is 0 or a very small number is thrown somewhere to some other position in that particular column. Now, in the second step, we repeat the same thing, but leaving the first row as it is. So, the first row is not used. The first row is not used. The second column is now searched. The second column is searched for the largest element in magnitude out of the n minus 1 elements. We are leaving the first element, over here, and then we are using only this n minus 1 elements of the second column. So, the second column is searched for the largest element in magnitude out of the n minus 1 terms in the second column, leaving the first element. We repeat the procedure in n minus 1 stages. So, repeat for n minus 1 stages. Now it may be possible that when we are searching for the largest element in magnitude, there may be a number of elements which are equal, say for example number of elements is 5 5 5. So then we will interchange with that one which comes first, that means the smallest j that comes there will be taken as the row at which we should interchange the elements. So even if we have the number of elements which are equal, we do not face any problem. Mathematically what this means is, let us write down mathematically, we shall choose a particular number j, that means that particular column we want, choose j the smallest integer choose j the smallest integer for which magnitude of ajk at any particular pivoting time is equal to maximum of aik of k for all k less than or equal to I less than or equal to n, and interchange rows k and g. We are now at the position of kk. Now this searches all the elements between k and n. So we are going below the pivot and then bringing that particular, we are finding that particular element the smallest integer, that is the nearest one that is there, that is what we discussed earlier. If they have number of elements equal, we would like to take that one which is nearest. So we take the smallest integer for which this relation holds and then interchange rows and k and j. So this is how we can program it when we are programming for finding the largest element in magnitude. Now this procedure is called the partial pivoting procedure. The remaining part is the same as the Gauss elimination procedure that we are doing it. The second type of procedure is called the complete pivoting. Now this I will describe this procedure. This procedure is not used because it is expensive. What we will be doing here is that when I start with this augmented matrix here, I am going to take this entire matrix A, find the largest element in magnitude of the entire matrix, bring that element, let us suppose this element is the largest here, I will bring that as the pivot here. That means it requires interchange of equations and interchange of columns. So if you interchange the first row with this kth row and then interchange the kth row with the first row, so that means first kth column with the first column, therefore we are interchanging both rows and columns. In other words, we are now shifting the variable xk to the position first position. That means it is also involving the solution vector in which we are exchanging x1 with xk variable also. So it involves both row and column interchanges. So let me just write down the first step. In the first step the entire matrix A is searched for largest element in magnitude. This element is brought as a pivot. The entire matrix A is searched for the largest element in magnitude, this element is now brought as a pivot. Now what does this imply? We will say therefore this implies or this requires interchange of columns and rows. This requires interchange of columns and rows. This implies that the location of the variables is disturbed. So this means location of the variables or locations of the variables are changed. Now let us suppose we have done this and we have gone to the next stage. What the next stage would look like? Now the first row is left as it is. Now I will be taking these elements of this n minus 1 into n minus 1 matrix in the second stage, again find the largest element in magnitude, bring that as the second pivot. So again this requires interchange of the second row with that row and then the column, this column with the second column. Now therefore a interchange that was made earlier, that means let us say variable x1 and x50 was interchanged earlier, again it is possible that the variable that is changed is again gets disturbed. Therefore we need to keep track of location when once the procedure is complete, where is the variable, in the which position the variable is now. X1 may not be in the x1 position, it might have gone to 100%, it might have shifted from 100 to 50, then it might have been changed the position. So we need to keep an index and then keep tracking where all these elements are there. Therefore the procedure is very expensive, because we will be comparing in the first stage n square elements, n minus 1 square elements, n minus 2 square elements and so on, and besides that to keep track of all these locations would be very expensive. Therefore this procedure is very expensive, and they have actually computed how the partial pivoting works vis-a-vis the complete pivoting, and it is found that complete pivoting does not score in any way better than the partial pivoting. So all the strategies that are adapted from the computer software would uses only the partial pivoting. Then if if you are writing a computer program for this procedure, what we would normally do is we take this augmented matrix as a n into n plus 1 matrix. So what I would take here is, this is an n into n and this is a n into 1. So B is taken as the n plus 1th column of A, that means you do not have to write down another array for B. So you can declare A itself as a n into n plus 1 matrix, you can define it, so that you identify the n plus 1th column as the right hand side vector and then proceed with the solution procedure, and then the first n into n elements will be the required matrix U, and then the right hand side vector is going to be Z. So that is how you can write down a program in a single loop, you can go and then do it. Now earlier we have discussed about consistency, inconsistency with respect to this augmented matrix. Let us just remember what we have said at this time. We said if rank of A is equal to rank of this augmented matrix and this is equal to n, then we have a unique solution. Then you have a unique solution. Then we have, if rank of A is equal to rank of A, the augmented matrix, is equal to some r less than 1, then we have got infinite number of solutions. We have got infinite number of solutions. Now in both the cases we call this as a consistent system. So in both the cases it is a consistent system. Now lastly, if rank of A is not equal to rank of AB, then it is inconsistent. So rank of A is not equal to rank of AB, then it is inconsistent, that means it has no solution. Inconsistent, that means it is no solution. Now these concepts that we have talked of should automatically be reflected in the Gauss elimination procedure that we are doing it. Let us see what do you mean by the infinite number of solutions case. When the system has infinite number of solutions, that would imply that there are number of rows which are dependent rows. Since it is a dependent rows, number of variables can be transferred to the right hand side, and then we can obtain the solution as 1 parameter family or 2 parameter family, or in general in this case n minus r parameter family of solutions. Therefore here this shows that there are n minus r rows which are linearly dependent. Now in our computation purpose, this would mean that we will have that many rows with zeros, because we are eliminating the procedure and we are able to Gauss elimination. Gauss elimination should automatically tell whether this system has a unique solution or it has the infinite number of solutions or inconsistent. Let us suppose I have two, let us say there are two dependent, let us say that there are two dependent rows, two dependent equations. So let us take the case when we have two dependent equations. Now when I perform the Gauss elimination using the partial pivoting, let us say we use partial pivoting, then all the zeros that turn up, because they are dependent equations, they would all be, we are subtracting the equation from another equation. So zeros would automatically produce. Therefore what happens is the last two rows will turn out to be 0 0 0 0. So the computer can automatically check the number of rows that it is having zeros by your index, and then these rows will then tell us that that many number of parameter family of solutions. So this will then tell that the system is consistent, 1, 2, the number of rows that zeros are produced is the order of the parameter family that we have. So in this case the system is consistent and it has got 2 parameter family of solutions. It has got 2 parameter family of solutions. Now you can see in this case, as we are saying, rank of A is equal to rank of the augmented matrix AB is equal to n minus 2. The rank of this will be n minus 2 and there are zeros. Therefore I have got n minus 2, that is 2 parameter family of infinite solutions that we have got here. Now if suppose this system was inconsistent, then what would happen here is I would get here something like this 0 0 0 0, it gets eliminated and you have some number, non-zero number over here. And now we have inconsistency, you can see that when you multiply by the vector x, this will be 0 is equal to a number. So what we would be producing is equal to 0 is equal to a number, that is what this implies. Therefore the system will be inconsistent. Therefore the computer would automatically look at this values and then say that when once you have a element on the right hand side, all these zeros, this system can be inconsistent system. Therefore this checking of the for unique solution, infinite solutions, inconsistency is automatically implied in the computer software. That one we must be able to introduce it. Now let us just take a problem corresponding to this, how it would will be able to say that the given problem is inconsistent. So let me take this as an example. Solve, if possible, the equations let me take these equations as x1, 2x2, 4x3 is 9, 2x1, 5x2 minus 3x3 is 9, 5x1, 12x2 minus 2x3 is 25. Use partial pivoting. Use partial pivoting procedure. Now let us write down our augmented matrix AB. So we will have 1 2 4 9 2 5 minus 3 9 5 12 minus 2 25. Now I search the first column for the largest element in magnitude, 5 is the largest element. So I will interchange row 1 and row 3. So I will now interchange row 1 and row 3. So I would therefore have 5 12 minus 2 25, 2 5 minus 3 9, 1 2 4 9. So, this is an equivalent matrix. Then the next step is, let us, as we have done in the previous example, let us make this element as 1. So, I would divide the first row by 5, divide the first row by 5, then this will be equivalent to, I will have 1 here, I will have 12 by 5 minus 2 by 5, and this is 5, these stay as it is. Now, we make these two elements as zeros. So, I need row 2 to be replaced by row 2 minus 2 times row r 1, row 3 replaced by row 3 minus row 1. So, I can multiply 2 times and subtract to get my new row, and multiply just subtract the first row from the third row, I get a 0 over here. So, then I will get the equivalent system. So, 1 12 by 5, 2 by 5 5, and then 2 times this, subtracting this is 0. So, I can just let us put these values over here. We are multiplying 2 minus 24 by 5. So, I will have here 1 by 5, 1 by 5. Then we have got this as minus 3 and minus this plus 4 by 5. So, that is minus 11 upon 5, get minus 11 upon 5. Then we are multiplying 2, subtracting, so I have minus 1 here. Then row 3 minus row 1, I have a 0 here, I have got 2 minus this, therefore, this is minus 2 by 5, 4, this is 4 plus 4 by 5, that is 24 by 5, 22 by 5, 22 by 5, then this is equal to 4. Then the first stage is over. Now, for the second pivot I will search these two elements for the largest element in magnitude. So, I need now an interchange between row 2 and row 3. So, I would now perform the interchange of row 2 and row 3, interchange of row 2 and row 3. Therefore, I will have 1 12 by 5, 2 by 5 5, and the second row becomes minus 2 by 5, 22 by 5 4, 0 1 by 5, minus 11 by 5 minus 1. Now, let us again make the element as second element as 1. So, I would divide throughout row 2 divided by minus 2 by 5. Then I will have 1 12 by 5 minus 2 by 5 5, 0 1, this is minus of 11 by minus 11, and this is minus 10, right, and then 0 1 by 5 minus 11 by 5 minus 1. Now, I make this 0. So, I would now row 3 is now replaced by row 3 minus 1 by 5 of row 2. So, I would produce 1 12 by 5 minus 2 by 5 5, 0 1 minus 11 minus 10, 0 0, and this is also 0, and this is you have minus 1 plus 2. So, I have a plus 1 here. Now, you can see that the procedure has implicitly shown that the system of equations are inconsistent, because I have zeros here and 1 here. Therefore, what we are implying here is that 0 is equal to 1. So, what we have produced therefore is an inconsistent system of equations. This is how inconsistency can be observed. We would also noted that since we are using partial pivoting, this particular behavior is thrown to the end of this last rows of the given augmented matrix. Now, a variation to this Gauss elimination procedure is what is known as the Gauss-Jordan procedure. So, let us just describe what this variation is. It is called the Gauss-Jordan method. You remember when we started the discussion that there are 3 matrices for which the solutions was trivial, that is when A is the form D or L or U. The Gauss elimination procedure has used the third one where A has been reduced to upper triangular matrix U. The Gauss-Jordan procedure follows that A will be reduced to a diagonal matrix D. So, we start with your augmented matrix AB, we perform the same elementary transformations. So, what we will having is a Gauss-Jordan procedure. This will now reduce to D of some Z. So, where D is a diagonal matrix, D is a diagonal matrix. Now, when once I have D diagonal elements, what is this matrix? This diagonal matrix is the form some elements over here that we have produced zeros over here and we have produced Z over here. So, I can divide by the diagonal elements each of these equations and then I can produce here from here I and x. So, when I once divide by these diagonal elements, I would produce 1 1 1 over here and that means simply this is I and this is the x. Therefore, this is our solution vector automatically coming from this one. Now, if this is the method, what is the difference between the Gauss elimination and the Gauss-Jordan is only this, that at any stage of elimination when we choose a pivot, the elimination is done not only below, but also above. So, if I take a pivot over here, I have got the elements below and above also. So, at each stage I will eliminate elements below and above the pivot, then that will automatically reduce to the D form, but if you are dividing by the element before the procedure, you will directly land up into I and x. Therefore, this implies that perform the elimination not only below the pivot, but also above the pivot. So, we will perform all the eliminations not only below the pivot, but also above the pivot. This gives us D, this gives D Z. Now, divide by the diagonal elements. Divide by the diagonal elements. Divide by the diagonal elements to give I x. As I mentioned earlier that if you are starting before the elimination, if you are making the diagonal pivot as 1, then this will automatically land up into the final format of I is equal to x. Now, this procedure looks attractive, but we will show later on that the Gauss-Jordan procedure is much more expensive than Gauss elimination procedure. So, this is expensive compared to Gauss elimination. There would be a substantial amount of difference in the amount of the operational count between the two methods. But then why do we need this method? Now, interestingly, we need this method for another thing, and that is in our last lecture we gave a simple example of a system of equations which you may have, wherein you would like to solve a system with different right hand sides. There if you have to use the Gauss elimination procedure or Gauss Jordan procedure, I have to solve each time, take the right hand side word, change it, again solve, change it, again solve. However, if I have the inverse of a matrix once, then independent of the number of right hand side that we have, we can use the same inverse matrix and find A inverse of B1, A inverse of B2, A inverse of B3 and so on, and find the solutions. So, in that case we need a procedure which can give us an inverse of a matrix. The Gauss Jordan procedure we have discussed can be used to find the inverse of a matrix. So, how do you, the simple thing that we do here is, I start with the augmented matrix A and I. I will start with the matrix A, the augmented with the identity matrix of the same order. So, this will be augmented matrix A and I. I would perform your Gauss Jordan, we will perform the Gauss Jordan procedure, then A is reduced as I, and hence I must be reduced as A inverse, because A inverse is equal to I, therefore, this gives me A inverse. Therefore, this Gauss Jordan procedure would give me the inverse of a matrix. Now, let us take an example for this. Let us take an example for finding the inverse of a matrix. Find the inverse of, let me take the matrix as 1 2 3 2 5 1 2 3 1. Using Gauss Jordan method. Now, let us write down our first step here, that is A and I, the augmented matrix A I. So, I will write down 1 2 3 2 5 1 2 3 1 and 1 0 0 0 1 0 0 0 1. Now, we R2 is replaced by R2 minus 2 R1 rho 3 minus 2 R1. So, we are making both of them as zeros. Then the first row stays as it is, the second row this is 0, 5 minus 4 that is 1, 1 minus 6 that is minus 5, this is minus 2 1 0. So, that is the second row. The third row is 0, 3 minus 4 that is minus 1, 2 minus 6 minus 5, minus 5, and we have multiplied this by 2, this is minus 2 0 1. Now, here both are equal. So, let us now I have to perform in the second stage a 0 here and a 0 here also. So, what we would do, row 1 is row 1 minus 2 times row 2, that will bring a 0 over here, and then row 3 is row 3 plus row 2. So, that will bring me a 0 here. So, we are performing both these operations at the same time, so that I have a 0 here and a 0 over here. Why we no we are not doing the partial pivoting, we are just doing straight away the Gauss Jordan procedure. Now, this will give us 1, subtract by 2, that is equal to minus 1, this is 13, this is 5 minus 2 0. So, I am multiplying all of them by 2 and subtracting them, oh sorry, right. Then second row stays as it is, second row stays as it is. The third row is row 3 plus row 2. So, I will have minus 10 minus 4 1 1. Now, before we proceed, I can make this element as 1. So, let us make this element as 1, row 3 is equal to row 3 divided by minus 10. Let us work backwards. So, let us also do, when once we do this by divide by 10 we have 1. So, let us write down what will be the next steps. Then we will perform row 1 is, we have made this as plus 1. So, we will make this as row 1 minus 13 times row 3, and then row 2 will be replaced by row 2 plus 5 times row 3. So, we have 1 here. So, let us first of all make this as 1. So, I will have this as 4 by 10, let us retain it as that, 1 by 10 1 by 10 this. So, I have divided by minus 10 throughout. So, I will have here 4 by 10 minus 1 by 10 minus 1 by 10 over here. Then I am now subtracting row 1 minus 13 row 3. Now, this is 1, this is 0, this is 0, 13 times this is 0. So, then I have here 5 here and minus 13 times 4 by 10. Is it right? That is 52 minus 50, that is minus 2 by 10, that is equal to minus 2 by 10. Then I have this second element as minus 2 and I am multiplying this by minus 13. So, that will be 13 by 10. So, that will be minus 7 by 10, that gives me minus 7 by 10. Then I am multiplying this by 13 and subtracting. So, I will have here 13 by 10, this is 13 by 10 from here. Then we go to second row 0 1, we have 5 times and added to is, therefore, this is 0. Now, let us take this element, this was minus 2, 5 times this, that is equal to 2, right, yes, that is equal to 0. So, this element is 0. Then I have 1 and 5 times this, 5 by 10, that is equal to 1 by 2, 1 by 2. And lastly, we are multiplying by 5, that is minus 1 by 2. Therefore, this is the required A inverse of the matrix. Now, if I want to solve the number of systems, I would then take it as x is equal to A inverse of B as the required solution if I am using it for solving a given system of equations. So, here we have been asked to just find the inverse, but however we could as well use this as finding the say solution system of matrix by finding the inverse of a matrix. So, I would you could use this A inverse and then find what the x is equal to A inverse of B. Now, very often it is found that the Gauss elimination procedure sometimes a little bit prone for round off errors, the way in which the computations are done. We can then have some alternative procedures which looks more attractive than Gauss elimination for the way in which it is done, but we shall also show that that method will be mathematically equivalent to the Gauss elimination procedure. Now, I will just give the brief introduction of that, we will take the derivation of next time. Those methods are called the triangularization. There are a number of names for it. It is called the triangularization method, and it is called the, some books call it as decomposition method, some other books call it as factorization method, factorization method, and some other simply call LU decomposition, call it a LU decomposition. So, all these are for the same method that we shall be describing it. Now, this method can be used for two purposes. One is we can solve this system, we can solve a given system of equations Ax is equal to b. We can also use this to find the inverse of a matrix. We can find inverse A inverse of A. So, this method can be used for finding the both the cases of finding the solution as well as finding the inverse of a matrix. The method is based on the fact that we can decompose a given matrix as the product of two matrices, one is lower triangular, the other is upper triangular. So, what we will write is we will write down A is equal to L into U. So, that is why you can see it is called LU decomposition. So, L is a lower triangular matrix, L is a lower triangular matrix, U is an upper triangular matrix. U is an upper triangular matrix. Now, let us just write down how it looks like. So, let us write down A11, A12, A1n, A21, A22, A2n, AN1, AN2, AN. L is lower triangular, therefore, it will be L11, L21, L22, Ln1, Ln2, Ln0. We have here U11, U12, U1n, UNN. The idea behind the procedure is simply that we multiply these two on the matrices on the right hand side, compare with these elements on the left hand side, and then obtain the solution for this. Before we do actually multiply and then compare it, let us just look one aspect of the number of unknowns that we have here, so that some simplification can be made here, so that this evaluation or computation of Lij's and Uij's are very simplified. And that observation that we shall make is that if you look at the number of elements on the left hand side, if you take A, it has got n square elements. It has got n square elements. Now, let us look at L. The number of unknowns, these are unknowns. So, number of unknowns are let us add them up. So, this will be 1 plus 2 plus 3 plus so on n, 1, 2, 3 so on n. So, these are the number of elements, that is your n into n plus 1 by 2. Similarly, if I take U, the number of unknowns here are the same. I can count from backwards. There is 1 in the last row, 2 in the second, n minus 1th row, n in the first row. So, the number of unknowns will be again be equal to n into n plus 1 by 2. Therefore, the total unknowns are the total number of unknowns are n into n plus 1, n squared plus n. So, it will be total of unknowns is this. When you multiply the right hand side and then compare it, the number of equations will be equal to number of elements here. So, what will be the number of equations will be n only. Number of equations is equal to n. n square. What does that imply? This implies that we have n arbitrary parameters, because there are n square plus n, and these are number of n square equations. Therefore, this implies that we have got n extra unknowns, that is n arbitrary unknowns. It has got n arbitrary unknowns. Now, this information, this is a very valuable information, that it has got n arbitrary unknowns, and we shall choose the values of these n arbitrary unknowns, so that the computation of this L and U becomes very simple for us. Now, there are two sets of values that can be chosen where this computation becomes simple is, therefore, we can choose either 1 Lii is equal to 1, or choose Uii is equal to 1. This is I is equal to 1 2 3 n, and I is equal to 1 2 3 n. Therefore, what we are really saying here is that if I just put this slide over here, we are saying that I would like to choose all these diagonal elements of L as 1, or all the diagonal elements of U as 1. Now, we would see, I mean we will do next time, that this particular choice of these ones would simplify evaluation of Lij's Uij's, because again by simple forward substitution we can get all the elements of Lij's and Uij's also from here. However, there are the names are there, so because the different authors have used it in different times and rather invented it, you can say. This first method, the called Doolittle method, it is after the author Doolittle, so it is named after him, it is called the Doolittle method, and Uii is one is called the Kraut's method. Now, both the ones are useful, because for analysis of the methods we would sometimes you take it as Lii is equal to 1 as the best way of writing it and then analyzing the methods, and for computational purposes both are identical. We do not, I mean there is no change in the solution or the number of operations or anything, everything will be identical, except that it is our choice which one of them we would like to use it. So, okay, we will continue next time.